Gentlemen, I'm really honored to give a talk on behalf of SESAME, the Synchrotron Light for Experimental Science and Applications in the Middle East. I will try here to address the history of SESAME, how was it established, and answer some of the questions posed by the organizers on the similarities between SESAME and the African Light Source and how SESAME got into existence. SESAME is located in Jordan. SESAME members and observers include Cyprus, Egypt, Iran, Israel, Jordan, Pakistan, Palestine, and Turkey, in addition to a big group of observers from Europe and the United States, China, Russia. SESAME is a regional center, and in addition to the benefit of science, SESAME also has major political impact on the politics in the region. As you see from the spectrum of countries, we still have countries who are still in conflicts with each other, Palestine, Israel, Iran, you name it. So despite all these political differences and even rivalries, SESAME was able to manage its way through, and we are really doing science. We are a third generation light source, where the project was originally perceived by UNESCO for a very obvious reason. UNESCO, as an advocate of international collaboration and in science for peace, SESAME's ideas was projected by UNESCO. And indeed, the reason a light source was chosen as a center for cooperation in the Middle East, it has first the ability to bring scientists not just from one discipline, from a group of disciplines scanning material science, physics, chemistry, life sciences, in addition to the fact that no single country in the Middle East can build a synchrotron light source on its own. So that's why international collaboration is an obvious way for countries with limited scientific communities and science budgets to build a synchrotron light source with wide spectrum of uses and users, and bringing about scientists from the different countries working together. So it has a very important political dimension in addition to its importance in grouping scientists together. There was a question on ESRF, how did it start? Actually, SESAME's story started gradually and slowly. There was a meeting in Dahab in Egypt in 1995 between some Egyptian scientists and Israeli scientists that they should work together on science, and science diplomacy was mounted on a wide spectrum. In 1998, the Middle East Scientific Cooperation Group agreed to build a project and seek support on the international level for its realization. Definitely, the synchrotron light source was chosen for the very obvious reasons that I have just mentioned. Hervé Chopper, ex-director of CERN, toured the countries of the region and talked to governments in order to convince them. And in 1999, UNESCO stepped in. Federico Mayor invited delegates from the Middle East countries for a meeting in which an international interim council was formed under the presidency of Hervé Chopper. So UNESCO became the depository of the statutes of SESAME, and SESAME effectively came into existence on 15th of April, 2004. Jordan was selected as the seat of the center in competition with 5 other countries from the region who later became members of SESAME. And the main selection criteria was that the host country should allow access to the center to all scientists of the world, that it provides the finance for the building construction, and the technical infrastructure, namely water and electricity, are reliable, and that the local authorities would guarantee strong support for the center once established. And this was really the case. The first proposal for the SESAME machine was to use an old BC1 light source that was disassembled and donated by the German government to the Middle East. And basically, it didn't make sense just to get an old synchrotron from Germany built in the late 70s and operating for almost 20 years and just reassemble it back in the Middle East. So something has to be done. The idea was to upgrade it from 800 MeV to 1 giga electron volt. And then, responding to users' demand in 2001, the Interim Council of SESAME delegated the technical director to work out in detail a proposal to increase SESAME's energy to 2 giga electron volt in order really to make it more powerful and more up to date. In December 2002, a joint meeting of the beamlines and scientific advisory committees advised to build instead a new machine with a much larger circumference than BESSY-1 with an energy of 2 giga electron volt and the possibility of upgrade to 2.5. And finally, the design was done at 2.5 giga electron volt because we wanted photon energies to reach up to 12 keV. Currently, SESAME is a machine running at 2.5 giga electron volt with a 133 meter circumference. In terms of beamlines, the scientific advisory group basically, based on users' demand and interest in the region, recommended the construction of 6 what we call phase 1 beamlines. Currently, 2 of these are fully operational, the X-ray fluorescence and X-ray absorption phase structure, which started operating in 2018, the infrared spectra microscopy beamline, which came almost a year later, and currently the material science beamline is in the final stages of commissioning, and we will start hosting users next month or probably beginning of the year. Currently, a macromolecular crystallography beamline is under design and construction. A soft X-ray beamline HESEB is under design and construction through ordination by the German government. And a tomography beamline BEADS is currently under design and construction through a donation or a grant from the EU. The 3 beamlines, the MX, the soft X-ray and tomography beamlines, are expected to be operational by the end of 22, early 23. As I've said, SESAME was commissioned in 2017. We started receiving the first users in 2018. The X-ray fluorescence beamline was the first beamline to host users in July 2018. 10 scientific papers have been published, mainly in areas related to materials, electric batteries, and also crystallography. The infrared beamline, we currently have 2 papers published in highly ranked international journals. As you can see, based on the proposals that have been submitted on the infrared beamline, they scan a wide spectrum from life sciences, archaeology, medicine, material science, molecular and cellular biology, atomic and molecular physics. So that's the real power of a synchrotron light source, which definitely, when we are talking about an African light source as a regional center for African countries, this would be ideal to really copy SESAME's experience into Africa and bring countries in Africa together. So in 2018, SESAME received the first call for proposals. 26 experiments were already done. And in 2019, 45 experiments were executed in 2019 using both the XRF and the infrared beamline. 12 papers have been published in international journals, mainly in material science and materials electronics, in energy, pharmaceutical and biomedical sciences, molecular and biomolecular sciences. And indeed, the impact of SESAME within the scientific community of the region is really being felt. Let me start by saying when SESAME was perceived and we called for the first users meeting, we only had probably around 50 or 60. Now, when we call for the annual users meeting, we get around 500 applications to join this meeting. SESAME, by all accounts, has boosted the scientific community in the region through training programs, workshops, individual trainings, EU projects through connected to EU, high performance computing centers, the Open Sesame project in terms of schools and workshops. We do convene an annual user meeting, usually held in November, but this year we couldn't hold it because of the COVID. And by all accounts, it has brought scientists from all the countries in the region, despite all the political conflict that have occurred and still occurring. We meet annually, and people from all SESAME member countries, scientists come in, discuss science. We meet twice a year, once in summer and once in winter in December, and all the member states come, despite all the differences that exist and still exist till today. SESAME allowed our scientists and staff to open up to the world in terms of fellowships in Europe, in the UK, in Soleil in France. And this photo shows the spectrum of users that come to SESAME, and it's growing by the year from few hundred to exceeding 600. And by all accounts, SESAME will have a socioeconomic impact. Particularly now we started seeing some applied research for the pharmaceutical industry in the region. I would close by saying that SESAME already is hosting some African countries. Indeed, Egypt, as a big African country, is part of SESAME for sure, as a Middle East and Arab country. Egypt is very active in SESAME. This shows that also beyond the Middle East countries, we have hosted users from Kenya, South Africa. We have some of our beamline scientists who are co-conveners of the Light Sources Group of the African Strategy for Fundamental Applied Physics, Jihan Kamel. Our scientific director, Andrea Lausi, is a member of the steering committee of Lab Initiative, partnering with IUPAP and IUCR to enhance the advanced light source and crystallographic sciences. And we have some of the African scientists who are participating in the design and construction of the beads and HESAP beamlines. I should mention also that during this conference, the MOU between the African Light Source and SESAME has been signed. So indeed, by all accounts, despite all the financial, political, and technological challenges, SESAME has been a victory of optimism over skepticism. I think the African countries should probably look at SESAME's experiment, and I see that with basically persistence and a good spirit of cooperation and opening to the other regions of the world, the African light source should come into reality, hopefully, within this decade or early next decade. Thank you.
Thank you very much. I really appreciate the talk. Given the time, I'm going to take privilege and ask my question and allow one question from the floor. So if you want to ask a question, be ready. The question I have is, even though you've really been operating such a short time, have you already seen the ability to attract people from your community, members from your country who've been outside, you know, in the East or in the West, to come back to participate in SESAME? Are you already seeing that, you know, reversal of brain drain?
To be frank, it has been a two-way traffic. We train many scientists through SESAME, and some of them, for example, now are working in European labs. Some of them are in ALPA, in Max 4. Some of them went to Soleil. So it has been a two-way traffic. But at the same time, this showed the value of SESAME. That's really training and qualifying world-class scientists who are able to compete for jobs and positions in Europe and the United States. And this is a good sign. But
that's a good sign.
by
I agree.
all accounts, it helped also reverse the brain drain, where now professors in the universities in Jordan and the region, really, those who studied in Europe and the US used to come and be cut off from their science, because to travel back to the US with the coast and so on, and sometimes to be away from family for 6 months or a year is difficult. So we could see by the growing number of users that it really helped retain the scientists, first to do their experiments in the region and to focus on coming to SESAME, which is half an hour or 1 hour traveling by plane, in addition to the fact that it opened doors for them to work with other colleagues in Europe and United States and Japan, while still retaining their positions in their own universities and institutes.
Okay. One question from the floor, maybe?
Yes, Gebret Tesma wants to know, what is the biggest challenge in construction that you faced?
To be frank, if I can tell you about the SESAME challenges, technological challenges were not really the case, because to be frank, we got a lot of support from our sister European laboratories, Soleil, Diamond, the Swiss Light Source, SAM helped a lot. So definitely there were technological challenges on the way, but these were circumvented because our scientists worked with the European scientists and the international scientific community and were able to circumvent. The real challenge that we had was financial. To be frank, and we are still suffering from that because of the political instabilities in the region. We always had to work with very tight budgets when it came to capital investment to basically redesign BC 1 machine from generation 1 machine to generation 3. So we had to come up with the money. We needed around 30 million euros, and we had difficulty in coming up with the money. And also in the operational budget, because some member states pay this year, next year they don't pay. So it's mainly financial. So our main challenge was financial, the money and the resources. Technological challenges, although they were basically big challenges, but they were circumvented because of the collaboration and indeed the hard work that the people here did in the design and operation of the machine, supported by their colleagues from Europe, US, and Japan.
Thank you very much.